Hello and welcome to Potential Difference, Current and Resistance class. I'm Laura Lewis and let's get started. So the first thing for learning objectives is state Ohm's law for ohmic conductors, describe ohmic and non-ohmic conductors, and use the equation voltage, current and resistance for in exam questions. Okay, so quite an obvious one. Okay, so Ohm's law. So what is Ohm's law? So I just want to get my notebook out. So the straightforward way is that voltage is directly proportional to current through an ohmic conductor. Okay, that's what you'll see as written in books. So just a straightforward statement like that. Okay, but you probably think, well, what is an ohmic conductor? That's a fair point, obviously. So an ohmic conductor. So I've drawn this diagram out. It's if you plotted the voltage and the current flowing through an ohmic conductor, so a component in a circuit, you form a straight line. So if you look at this, you can see the current goes up at the same rate as the voltage. So you can say that voltage is directly proportional to current. Okay, so in an ohmic conductor, so voltage is directly proportional to current. Okay, directly proportional to current. Because there is a straight line. So as one goes up, the other goes up too. Okay, so that's what that really means. So for ohmic conductors, okay, so ohmic conductors only, we're talking about for the moment. We'll talk about non-ohmic a little bit later. You have the equation, a very familiar one. I'm sure you will either come across it or you'll definitely come across it at some point. V equals I times R. You may see this rearranged, it's the same equation, but it's always voltage, sometimes known as potential difference, equals current times resistance. And voltage is measured in volts, current is measured in amps, resistance is measured in ohms. Okay, it's a Greek letter omega. Okay, so components that are ohmic are usually resistors. Okay, standard resistors are usually ohmic, but lots of things aren't. Okay, this is what we're going to catch people out. A lot of things aren't. So a filament lamp. So a filament lamp is the same basically as a light bulb. It's one with the metal filament in it. That's why it's called a filament lamp. If you think of like an old-fashioned light bulb, that's a filament lamp. So actually, if you plot this, as voltage goes up, it starts off ohmically, and then it will do that. Okay, so if you get a graph like that in an exam, that's usually pretty much nearly always a filament lamp. Okay, what's happening here is the current kind of evens out due to it becoming hotter. So as current increases, and so as current increases, resistance increases because of the heat. It gets very hot. Okay, due to heating. And this is actually classed as non-ohmic. You can say that that portion was, if you did about what portion of the graph is ohmic, but it won't be overall. It won't keep going on forever like that because it'll get too hot and possibly even melt at some point. Light-dependent resistors. It's another one. So light-dependent resistors, as the name suggests, they're sensitive to light. Okay, but in this case, as the light gets brighter, the current goes up. Okay, so it varies upon light, not on the voltage through it. So they're just a different type of component. They're not ohmic, they rely on light. Okay, so you may have them in things like night lights and street lights. They could be LDRs, often they're known. Okay, but they're sensitive to light. Okay, it's a little bit different component. Another one, a thermistor. So used in thermostats, senses temperature. So thermal thermistor is quite a good one because its name tells you what it is. And this one behaves kind of in the opposite way to filament lamp. The higher the temperature, the more current flowing through it. So these two things can look ohmic, but they're not, because they're not voltage and current. They are temperature and light. Okay, so they're one things to watch out for. Okay, so we'll do a little bit of practice with ohmic conductors. So if a current of 2 amps flows with a resistance of 5 ohms in the wire, what is the voltage? So we write out V equals IR. Remember, always write out the equation. Okay, V equals I times R. This carries on from that sign. So V, we don't know V. I is 2 amps. Nice and easy, isn't it? 2 amps times 5 ohms. This is going to be very simple, straightforward. V equals 2 times 5 is 10. 10 volts, okay, because the symbol's the same for voltage and its units, not always, so the power current and things. Okay, so if a voltage of 30 volts passes through a component with 10 ohms resistance, what is the current? So again, we'd write out the equation. This time we need to rearrange. We need to make I the subject. So divide both sides by R. So it's V over R equals I, because in maths we call making the subject. It's exactly the same process here. So we've just divided both sides by R. Now we put numbers in. So V, 30 volts, resistance 10 ohms, okay, equals to I. Okay, 30 divided by 10 is 3. So I equals 3 amps, okay. So last one, if a 1 amp current flows with 2 volts, okay, voltage, I should say, what is the resistance? So again, V equals IR, okay, or I times R. So we know V, okay, so I'm going to do it differently. So I'm going to put numbers in first, 2 volts. I, okay, so I is 1 amp. And we don't know the resistance. So this time we divide both sides by 1. Okay, so 2 volts divided by 1 amp equals R, and R equals 2 ohms. So thank you for listening to the video. Hope to see you in another one. Thanks for listening and goodbye.